Did I tell you that community level interactions include food web stuff? There's the trophic and the non. Okay, great. I apologize again for that mix-up. I'd like to do our warm-up for a couple of minutes. I'm not a math teacher. I'm actually a horrible math teacher. I can perform math, but I don't have the right lingo to explain math. But I do want to spend a couple of minutes on this rule of 70 thing. If you're copying, please take a moment to focus on this. You can go back to that copying later. You will need the rule of 70 on the AP test because biological populations grow exponentially instead of linearly. And because you can't use a calculator to do it this way, all of the College Board's population growth questions come down to doubling time and growth rates. There's only two variables in this equation: how long it takes to double and what rate these populations are growing in. So here the growth rate is 5%. You don't even need to know the starting value to figure out how long it takes to double at 5%. Make sure that you have this in your notes. There's a really critical step that I just did. To use the rule of 70, you can solve for doubling time, but please look up. You write the growth rate as a percentage, not as a decimal. Make sure that's in your notes, that you have to write the growth rate as a percentage. So if it's 5%, you just put it over a 5. Students will sometimes translate that into a decimal, and that's a mistake. So we can figure out how long to double. 70 divided by 5 is 14. So you go from this to twice that in 14 years. The doubling time is 14. In other words, if you had $1 in the bank and 5% interest rate, that would become $2. It would double in 14 years. Now you'll notice that my question asks you how long to quadruple an octuple. If we go 14 years more, what's happened to our $2 in the bank? It's another doubling time, so we're going to double. What's 2 doubled? 4. So you would quadruple that starting value in 2 doubling times. It'll double to 8. So you could have 8 times what you started with in 42 years. There's a thing about exponential growth that's sort of unintuitive sometimes. In these 14 years, you made a lot more money than in these 14 years. Because you're growing by a percentage of the total amount in that account, the more you have, the same percentage of a bigger number is more growth. 5% of $1 bazillion is a whole bunch of dollars. So you grow by more per year the longer you wait. You probably know this about checking accounts and savings accounts and stuff. to teach you math, because I know how I can do it, but I don't know the right lingo to explain it. If you have a question, I'll try my best. You want to ask me anything that doesn't make sense about this? I see that many of you are quitting. It looks like you were dying on the inside. I would try to help if you could articulate a question. We'll just all die quietly. Yes.
For the starter, is it .521 or is it $521?
No, I mean, it was just $521. And by the way, I just used an arbitrary number. That number doesn't matter. That could just say X dollars. It's still the same doubling time. Right? Because all you're going to calculate is the doubling time, not the totals. Yeah?
So it'll take 42 years to go off control?
That's right, yeah. To go from whatever you started with to 8 times that is 3 doubling times. Yeah. 2 to the third is 8, right? Anybody else? Yes?
Can you go over the abiotic cycle?
I will spend about a half hour on this. Anybody else want to ask me something about the warm-up stuff and the rule of 70 stuff? Okie dokie. We had a couple of study goals left in 2.1, but I want to leave those for later. We did positive and negative feedbacks already. So I'd like to leave the 2 remaining study goals in assignment 2.1, and I'd like to start on 2.2 today. Sienna, you're recording or streaming?
Yeah. Assignment 2.2 had about a dozen vocab terms and then about 5 study goals. There was one that you skipped on there. It's crossed off in your study guide. First on the vocab, there's a couple of vocab terms that I want to leave until tomorrow because they'll be better explained as part of a study goal. So, skipping the nitrogen cycle vocab, are there any other vocab questions on assignment 2.2? This is the chapter 7 vocab. The chapter 7 vocab. Vocab question on chapter 7. Yes? Drainage basin?
Another word for a watershed. So it's an area that all drains to the same point, aka a watershed. Other vocab? Yes?
Nitrogen fixation.
We'll do all the nitrogen stuff in study goal blah 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 tomorrow. I think that's study goal 18 maybe? 19? Yeah. We'll do that one tomorrow. What else? Yeah?
Upwelling?
So, upwelling is when cold water comes up from the bottom of the ocean. I'll make you a bad diagram. So when wind, who asked, Kyler? When wind blows offshore, that water is pushed along with it, right? And so because that water is leaving, it has to be replaced from somewhere. And so you get cold, nutrient-rich water welling up at the coastline. It's called upwelling, and it's really important because cold water holds more dissolved nutrients, so it's more productive. You always want to fish where there's upwelling because there's more algae, so there's more little bugs, so there's more little fish and big fish. Upwelling is cold, nutrient-rich water drawn by offshore wind. Other vocabs? Okay. Study goal 11, I kind of want to skip it. Unless there was a specific question on it, I wasn't planning the lecture. I do get a lot of confusion about number 12. Please look up. Biogeochemical cycles are all the chemicals moving between the atmosphere and the hydrosphere and all of us and the rocks. And the second part of the question says, for those 4 layers, how long do chemicals spend in each? And you don't answer that with a number. These are relative. So if you don't have this, you should add it to number 12. Chemicals cycle through the atmosphere very quickly. Through the biosphere, a little bit more slowly. Hydrosphere, sometimes very slowly, because water can move very slowly. But once something gets into rock, those chemicals will stay in that rock for a very, very, very long time because the rock cycle is so slow. So, very fast, very slow. Potentially pretty fast and potentially a bit slower than that. These are relative terms. Oh yeah.
I have a question for 13, like real quick.
Go ahead.
I couldn't find what sulfur does.
Used in amino acids, I believe. I do have this in my notes. I can confirm. Kids have asked me in the past. Yeah, amino acids. Building blocks of proteins. For number 14, I just need to do a quick little survey out there. How many of you have already taken chemistry? That might be the wrong question. How many of you either didn't take chemistry or took chemistry but retained nothing? Okay, so for those of you that just raised your hand, if you didn't take chemistry or you survived it somehow but have no idea what happened, you do not need to be chemists to do apes. If you're going to be a scientist, you'll need chemistry sooner or later. There's really no sciences without chemistry. It's very important. But for apes, you could get by without any chemistry as long as you can learn that chemistry happens. You don't have to understand why. Or even how, the nitty-gritty of all this, that's not important for apes. But I'll show you the amount of chemistry you'll need for this class. You would have to know, for example, that that's carbon dioxide and that's water and that's oxygen gas and that's glucose or sugar. That would just be memorization, I guess. You would also need to know that there's this thing called photosynthesis where blah, blah, blah turns into blah, blah, blah. You have to just know that. Not explain how to balance that reaction or where the electrons are shared, how much. So you don't need to know the chemistry of
this stuff, but you do need to know this much happens. If you've never had any chemistry, you'll survive, but it'll feel like more memorization, I think. This is the first unit where we have a bit of chemistry. There's more and more of it coming in later units. I mostly wanted to spend today on 17, but I need to check in really quickly on rock cycle stuff. Like this. Please look up. The big yellow circle is biogeochemical cycling. Stuff goes from the atmosphere to life to water to rocks and back. When things become rock, plate tectonics move them around, the rock cycle delivers them up to the surface, and erosion and weathering takes stuff out of rock. How many of you feel like you've seen these words or these concepts before in your education life? This is the part that's tricky for me. Because I just talk about this like everybody's familiar and you're all like, yeah, I'm totally familiar. But then when I drop one of those words on its own separate, kids are like, wait, what do you mean? And then I have to like go back and baby step it. So if you have any struggles along the way, when I talk about this cycling, you really should interrupt me and ask. How many of you have seen plate tectonics before? This type of boundary is divergent. This type is convergent. And this type? Transform. Do you all know that rocks weather and erode into sediment? And that sediment can be deposited and turned back into rock. Tight. Check out this rock. This is in the Santa Barbara Hills. Many years ago, I used to spend a lot of my afternoons on this rock. It is. It is. You recognize the road or you recognize the feature?
That's where my dad does search and rescue training.
Say what now?
That's where my dad does search and rescue training.
At Gibraltar. I didn't know that. Cool. He's local search and rescue?
Yeah.
Tell him thanks for volunteering. Or is he a sheriff's agent that actually runs?
No, he's a volunteer.
He's a volunteer. Tell him thanks for volunteering. All right, check this out. If you look at that lady's feet, you can see these curving lines in the rock. My hunch is every single one of you has in your lifetime seen what made this rock feature. You've all witnessed what made those curved lines. Does that look familiar to anybody? What does it look like to you? It might help if I do this. Yeah.
Sand?
Sand? Yeah, sand and where?
In the ocean? Water?
Yeah, in like shallow water. How many of you have seen where like little wind on a curving coastline makes those little ripples in shallow water and sand? So this used to be sand in shallow water, like it appears. And I don't know the details, but I do know that the chemistry of that water changed. And all that sediment, that sand, was locked into that shape because it hardened into rock relatively suddenly. It was either buried by a different type of rock that had a different composition, or I've heard that a really common thing is that a whole bunch of ashes came into that water and changed the pH of the water. At a different pH, all that sand is kind of bonded to itself. I'm not an expert in all these possibilities, but I do know the story of this particular rock. It was once a shallow bay. That shallow sand firmed up into rock, and then over a noble tectonic time, that plate smashed up against another, tipped up near vertical. The other layers have washed off it, and now that harder rock is still there as Gibraltar rock on the backside. There's this one little section that has these little ripples on it that are from the bottom of the ocean. The process of turning sediment into rock, please look up, is a vocab term you'll need later. It's called lithification. Turning sediment back into rock. If you look at the upper arrow, sediments can be deposited and turned into rock. Rock, of course, can weather and erode back to sediment. I am available for questions, but I really want to talk about number 17, so if you have a question, ask it now. I'll assume we're done with 2.2 after today. I just really want to focus on 17, which is the last study goal in 2.2. By now, how many of you have copied this part of the drawing? By now, how many of you have copied this part of the drawing? It'll stay on the board through all of tomorrow as well. So there's no urgency. It's better that you improve and annotate your drawings than just rush to copy them. So let's try to add some stuff to your drawing. First, please look up. Here we have a wacky little planet that takes CO2 from the air and water from the soil, uses sunlight energy to rearrange those ingredients as oxygen gas that it breathes out into the atmosphere and sugars that it usually stores in its tissues. That process is called photosynthesis. These things go in, these things come out of photosynthesis. How many of you saw this already because you had 8th grade science or something? There's a similar but opposite process where stuff like this happy human will take glucose from stuff that we eat, use oxygen in the air, tear up that glucose to release energy, and cough out leftovers like CO2 and water. That's called cellular respiration. You probably saw that in that same class at that same time. I don't have very much to add, but I do have one little detail that seems to be lost. When I was taught this, I was taught that plants do this one, animals and stuff do this one. And I was sort of surprised that there is such like an elegant, friendly relationship where these plants give me all the sugars I need. Thank you, plant, you're such a bro. But children, why would the plant bother to make sugars in the first place? If they can get energy from the sun and use that to make chemistry, why do they build sugars just for me? Like, thanks, plant, but why did it do that? Yeah?
Because they get the organisms that benefit from the oxygen breathe out like carbon dioxide, and that benefits them.
So you would think that maybe like it's just to get CO2 back from other animals or something, but you would still have a whole bunch of CO2 in the atmosphere anyhow. And I don't think so. I don't think that this is all about being eaten. It's not in the best interest of the plant to be consumed. Yeah.
To like pollinate the...
So they could still breed without being eaten. Like, why do they make this sugar?
They also do cellular respiration.
And that's the big whoop that I think we forget a lot of the time. Please look up. My cellular respiration includes the plant because the plant needs energy all day long, but there's not sunlight all day long. For most of my students, this is new information. If you didn't know this, you should definitely put it in your notes. Plants do photosynthesis during the day, but there's winter, there's time when they may not have leaves, and there's every single night when they're going to use those stored carbon bonds themselves. They do cellular respiration at night in the winter when they're leafless. They don't make the sugar for us to get the energy. They make those sugars to store energy for themselves. At night, plants breathe oxygen and give off CO2 just like we do. Plants have both photosynthesis and cellular respiration. All we get is the cellular respiration part, not the photosynthesis. I'm bonking too. I feel your sleepiness. I'm assuming that this is mostly review. Biotic means the carbon cycling in life. Anybody want to talk more about this? Now comes the part of the carbon cycle that I think might be new to some of you. This is the part where I think you would need to add a lot of notes. This is how carbon cycles through life, but sometimes carbon leaves the biosphere. It's important to point out that when that human is stabbed through the heart or the flower has died in its pot, those carbon bonds will be decomposed and recycled back into life most of the time. But in very rare cases, water might carry these into rapidly accumulating rock, and you might end up with some organic material trapped in rock layers. You should know that's very rare. That's called a sink, where an ingredient has left the biotic cycle and been stored away as rock. You could imagine like a shallow coastal area with a bunch of decomposing organic material. All of a sudden there's like a landslide and you get a whole bunch of rock layer on top. Now you've kind of trapped that organic material. It has left the biosphere, and over a long period of time, that will turn into rock, and you've got rock with organic ingredients in it. I need to be really, really clear about something. This does not happen all the time. Most rock does not have significant organic volume in it. Most rock is just made from little pieces of rock. But in some rare cases, it's like a fluke, a strange exception in geology. Some rare cases, you get this little layer of organic material in between other layers of rock. We're going to talk a lot more about how this happens later. So for now, let's just say it's an unusual thing in geology. If you could please look up, those rocks will eventually get moved around, smash into other rocks, and they'll either erode or weather from wind and water. Maybe some magma will push through. And if you could look here, that organic material would gradually be reintroduced to life some gazillions of years later by volcanoes or by erosion. Whatever gets buried in the rocks will always cycle back. Everywhere on the planet, new rock is being made, and everywhere on the planet, rock is wearing away. So these rare ingredients that sink into rock layers will, in rare events, very gradually trickle out. But there's one part of this story that's especially important for us today. There's one last little punchline that I have to rush toward. When that carbon is buried, the heat and pressure added by all of these rocks click all of that carbon together into longer and longer carbon chains. If you had like a big bag of Legos and you start massaging it at random, a few of those Legos would start to connect, right? Likewise, when you have tremendous heat and pressure, organic compounds in that rock will get clumped into longer and longer chains. Just like massaging a bag of Legos, you'll randomly start to click a few together. And humans figured out that if you can find those bunches of carbon stuck together, you can burn them and get all that energy out. We started with coal. Then we moved into petroleum. Check out, some smart person figured out that if you make a hole in the ground, and you get lucky about where you made that hole in the ground, some petroleum would come shooting out of that, and you can say yeehaw, and you can capture that petroleum in a barrel, and you can do some fancy shenanigans to turn that petroleum into something like gasoline that you can put into your car, and then do some more fancy shenanigans with your car so that you go vroom. And inside your motor, we're going chop, 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 chop. And breaking up all those little carbon bonds, getting all that energy out, that's what makes your car run. And of course, that's taking that carbon that used to be buried underground and is adding that to the atmosphere. It's very difficult to explain this early in our class, but I need to introduce now just one little concept that we're going to come back to over and over this year. It's not about the biotic carbon cycle, it's about the abiotic. There is just a teeny little bit of carbon at any given time being made into rock on our planet. Most carbon stays biotic. There's just a little tiny bit, you could call it leakage, of carbon that leaves the biosphere and enters the rock cycle. That's just a teeny little smidgen of our global carbon. And hundreds of gazillions of years later, that will trickle back out through eroding rocks and the rare occasional erupting volcano. We need to be really, really clear. This is a trickle of carbon that's leaving life and going into rock. And elsewhere on the planet, there is a trickle of rock carbon coming back into the life cycle. But humans have worked a really strange trick. We've rushed, we've accelerated just one part of that, getting the carbon out of the rocks and bringing it into play. We have almost exactly doubled the CO2 in our atmosphere compared to where we were 150 years ago. we're taking carbon that would have trickled out over millions and millions and millions of years, and we just took it all out of the rocks and we lit that stuff on fire, and now there's more CO2 in the atmosphere than we've had for a very, very long time. And that's all of a sudden. We have not accelerated carbon becoming rock. We have accelerated rock becoming carbon in the atmosphere. Where both of these used to be really slow, gradual processes, we've dramatically accelerated this one. Our whole world runs on fossil fuels. We all do it all day, every day. I'm not trying to say you're the bad guy. I mean, my car runs on fossil fuels too. My house runs on fossil fuels. We all do it. Questions on carbon, carbon cycle, the biotic, the abiotic carbon cycle? I am preparing to stop class. Anything on 2.2? Sienna, will you stop the screen, please?